In this video, we are going to learn about the complex plane. Let me remind you that the set of complex numbers, C, consists of all numbers of the form x plus yi, where x and y are real numbers. And we have also seen that real numbers can be represented on the number line, on the real line, and in the same way, complex numbers can be represented on a two-dimensional plane, the complex plane. So this is how we can represent complex numbers visually as points on a plane. We'll use these coordinate axes to measure out x on the horizontal axis, which we'll call the real axis. And we'll give it a label RE. And we'll use the vertical axis to measure the imaginary part of our complex number. So this is going to be called the imaginary axis. So 0 is right there at the origin, and an arbitrary, well, the label for the imaginary axis is IM. So an arbitrary complex number would be just a point in this on this plane, and it would have a horizontal coordinate of x and the vertical coordinate of y. So this point represents the complex number x plus yi, and we could also draw the vector connecting the origin to that point representing z. Okay, so now we can use the complex plane and this visual representation to understand these various operations that we've been doing with complex numbers. So for example, the complex conjugate of z, remember that is the number that is denoted by z bar, and it is x minus yi if z was x plus yi. So there is this sign flip for the imaginary part, meaning that the sign flip amounts to a reflection through the horizontal axis. So our complex conjugate will have the same x coordinate, the same horizontal coordinate, but the opposite, the negative of this vertical component. So this is where the complex conjugate of z would sit, being reflected through the real axis. So this is complex conjugation, but in a similar way we can talk about the addition of two complex numbers using this visual representation. So if we want to add two complex numbers, we'll first, in the complex plane, we'll first draw these numbers in the plane. Let's say z1 is there, z2 is over there, and draw these vectors connecting the numbers, the points representing the numbers to the origin, to 0. And then what we'll do is we'll use the parallelogram rule to add these vectors, and this means that we shift the vector corresponding to z2 to the end point of the vector representing z1, and similarly we do this with the vector representing z1. We shift it along the vector of z2 to obtain this intersection point, and that will represent the sum of z1 and z2. So that point, the vector pointing to this point will represent the sum of Z1 and Z2. Okay, so there's this very nice parallelogram rule to find the sum of two complex numbers in the complex plane. And so finally, to test your understanding, I would like you to consider the following. So let's look at the complex plane once more with the real and imaginary axes, 0 being at the origin. Let's measure out some units of distance. So that's 1 unit of distance, that's 2, 3, and we do the same along the vertical axis, the imaginary axis. So you can imagine having a nice coordinate axis this way. And I want you to take the complex number Z1 to be 1 plus 2i and Z2 to be 3 minus I, and I want you to calculate the sum of Z1 and Z2, then take its complex conjugate and put this complex conjugate on the complex plane. So where is it in the complex plane? And I'm going to give you a few options. So I'm going to, the first option I'm going to give you, I'll label it with A. So this point would be A. This point over here is B. Okay. Then my next point would be over here. This is point C. Okay. And finally, down 1 unit of distance from the real axis, here is point D. So I want you to calculate this sum, take its complex conjugate, and decide which of these 4 points is actually representing that number. Okay, so I hope you paused the video and calculated this number first to be 4, then plus I, complex conjugated, giving you 4 minus I. And if you look at the diagram, you have to go 4 units of distance to the right to arrive at 4, and then go 1 unit of distance down to have the number 4 minus I represented. Okay, I hope you got this right, and I'll see you in the next one.